Hello, my name is Bernard Piet and I'm an associate professor in the Department of Mathematics at the University of Durham. The aim of this video is to explain some properties of the COVID-19 virus epidemic and explain a few properties which takes most people by surprise. Why is the number of reported infections and deaths increasing so rapidly? Why does it take so long for the measures that have been taken to have a noticeable effect? How and when can the epidemic end? Viruses are very small, and when they penetrate our body, they invade some of our cells, lung cells for COVID-19. Then they use the metabolism of those cells to duplicate themselves in large numbers and invade more cells. When in sufficient numbers, the tiny water droplets that we exhale contain the virus, and these can carry the virus to other people who then become infected themselves. The illness evolved in several stages. At the beginning, our body does not know the virus as it is new to us, and we are all susceptible to contract the disease. When the virus enters our body, we become infected, and we refer to that time as day zero. After a few days, we become infectious, meaning that we can transfer the virus to someone else. Shortly afterwards, one can develop the symptoms such as temperature or a cough, but many people do not have symptoms at all. After 2 to 3 weeks, one usually recovers and becomes immune to the disease, but a small number of people, about 1%, will die. Finally, it is believed that the immunity to COVID-19 will only last for a few months, meaning that after that period we'll be susceptible to contract the disease again. This is why many laboratories are actively working to have a vaccine ready for the winter 2020-2021. COVID-19 is very infectious, as it is believed that on average every infected person will infect at least 3 other individuals, each one of which will also infect another 3 persons on average, inducing a chain reaction leading to a large number of infections rapidly. How can we characterize the epidemic progression? 2 parameters are commonly used. The first one is used mostly by epidemiologists, and this is the number of persons that each infected individual will infect on average. The second one, which is easy to read from a graph, is the number of days required for the number of infected people to double. These 2 parameters are related to each other, and one can use either of them. At the outset of the epidemic in the UK, data shows that the number of infected persons doubled every 2 days. So here is how it works. On day 0 we have 1 infected person. By day 2 we have another one, bringing the total to 2. On day 4 we have another 2 infected persons, bringing the total to 4. On day 6 we have a total of 8 infections. On day 8 we have 16. On day 10, 32. On day 12, 64. On day 14, 128. 2 weeks later, on day 28, the total exceeds 16,000. Then by day 48, the number exceeds 2 million. And by day 52, half the UK population is infected, with 500,000 fatalities. This is what would have happened had we not taken some protective measures to slow down the epidemic. Rather than listing numbers, it is more informative to present these figures as a graph. If we do it the usual way, it looks as if nothing happened much for several weeks, until it suddenly increases very rapidly. This is because the scale of the graph is not suitable to illustrate such a fast growth. To illustrate the epidemic better, we use a graph representation where all the power of 10 are equidistant on the vertical axis. This is called a logarithmic plot. On such a graph, an exponential growth is represented by a straight line. The top blue line corresponds to the population of the United Kingdom. We can clearly see from the figure that the number of infections is multiplied by 10 every 6 days or so. When the number of infected people become close to the total population of the country, the curve slows down and eventually starts to decrease because infected people heal or die. It is easy to understand why. At the beginning of the epidemic, the infected people meet mostly people susceptible to be infected, and so the number of infection grows rapidly. Towards the end, on the other hand, most people in the population are healed and immune, meaning that infected people are far less likely to meet individuals who can be infected. This is what is referred to as herd immunity. But what does control the rate of infection? There are two main factors. The first one is the virus itself, in its ability or resilience to be carried between individuals and to infect people. Unfortunately, the virus is as it is, and we can't change anything about it. A vaccine would prepare our bodies to fight the virus when infected, but none are available yet. The other factor is the type and number of interaction we have with other people. Each time we are in close physical proximity with someone infected, there is a risk of becoming infected. Objects that we touch or share also present a risk of infection. This is why the confinement measures were imposed and why we are asked to wash our hands regularly. Now let us look at the actual data for the United Kingdom. The first COVID-19 case was confirmed on the 31st of January. But data shows that the first few infections were well contained and that the epidemic only started a few days later, around the 3rd of February. 2 weeks later, in other words on the 17th of February, the number of recorded cases was 9, not the 128 that we predicted. Did we make a mistake? We didn't, and the reason is as follows. First of all, not every person showing symptoms is being tested. Moreover, the first symptoms appear after a few days, 5 on average, and the tests are often performed several days after the first symptoms have appeared. On top of this, many infected people do not have any symptoms at all. This implies that the number of recorded cases is not a good set of data for analysis, and that we should instead use the number of fatalities, which is recorded more systematically. So let's go back to earlier estimation of infection numbers. On day 14 there are just over 100 infected people, and if we use 1% as the estimated percentage of people killed by COVID-19, it means that on average one of these people will die. It can also be shown that on average the time of infection of these 128 individuals is day 12. The unfortunate person will die on average after approximately 20 days. During that time, the 64 people who are already infected by day 12 will double in number every 2 days, 10 times in a row, implying that by day 32 there will be just over 65,000 infected individuals. This shows why we can claim that the number of infected people is much larger than the number of cases that have been recorded. Indeed, the first fatality was recorded in the UK on 6 March 2020, and on that day there were 113 cases recorded, much less than the 65,000 we predicted. This is good news, as it implies that most people infected by the virus have minor symptoms. The argument we have presented here is very approximate, so can one make better, more accurate prediction? To better analyze the epidemic and propose measures to control its infection rate, we can use mathematical models. They use similar reasoning to the one we have just described, but expressed in more precise mathematical terms. In particular, we compute the number of individuals who are at each stage of the infection, taking into consideration the duration of the incubation, how infected individuals are contaminating others, and the time before patients either recover or die. The main parameter of the model is the doubling time that we have already described, and we adjust it to fit the fatalities data. We can then represent graphically the actual data and what the model predicts. On this figure, the red dot corresponds to the recorded death in the UK. The purple line is the number of fatalities predicted by the model if the doubling time was 2 days and did not change at all. The blue curve is the number of infected people predicted by the model. We notice immediately that around the 20th of March, the curve for the fatalities bent down, and one can show that the doubling time increased from 2 days to 4 days. This means that the epidemic has slowed down. This is the result of the precaution that we started to take around the beginning of March, washing our hands, refraining from shaking hands, etc. It took 2 to 3 weeks before the effect was noticeable in the number of fatalities. On these figures, we also plot the number of recorded infections as large blue dots, as well as the number of contaminating people as predicted by the model. Notice that it is difficult to relate the two together. We can now use the mathematical models to look in details as to what would have happened for different scenarios. First, if the confinement measure had not been taken at all, we see that the number of fatalities would have been over 500,000 in just over 2 weeks. Moreover, the rapid increase in number of very ill patients would have made the health services completely oversaturated, and most of the virus victims would have died at home without any medical assistance. Funeral services would also have been totally overwhelmed. Doing nothing was definitely not an option. In the United Kingdom, confinement measures were taken on the 18th of March, and as we speak, it is too early to find out from the fatalities data what impact it actually had. Instead, we can consider several possibilities. We should insist that the data we present here should not be considered as prediction, but just as illustration of what could happen next. Ultimately, it is the efficiency of the confinement measures, as well as how well they have been observed, that will decide the outcome. If the effect of the confinement measures is poor, then the model shows that there could still be a very large number of fatalities, but spread over a longer period of time, and still put the health services under intense pressure. Moreover, the epidemic would last several months, possibly well into 2021. If, on the other hand, the confinement measure slows down the epidemic drastically, the number of fatalities could ultimately be no more than 20,000. And at the same time, the health services will be under far less pressure. The epidemic would probably still last for several months, possibly until next fall. But this is not the end of the story, as the British government has asked all the people who are most at risk from COVID-19 to self-isolate more strictly than the rest of the population, and do so for at least 3 months. If well implemented, it means that people most at risk will contract the virus more slowly, and so the number of people admitted to hospital will decrease substantially. This could ultimately allow the government to lift some of the confinement measures. This would allow the epidemic to progress faster and move the end of the epidemic forward, while keeping the number of fatalities to a few tens of thousands. The health services will still be able to cope with the number of hospital admissions, and the epidemic might end sometime during the summer 2020. The data presented here should not be considered as valid forecast, as we do not know how much the vulnerable people are protected by this specific confinement. There are indeed several caveats. A few percent of the fatalities are of people with no prior medical condition, or in other words, people who are not known to be at risk and so do not take any specific protection measure. The big problem for the decision maker is that finding measures which lead to a manageable infection rate is very difficult. This is not helped by the 3 weeks delay between the implementation of new measures and the effect showing in the data. It is a bit like driving a car which would have a 30-second delay between the steering wheel being turned and the moment the wheel of the car actually starts to move, and without knowing by how much they will do so. These measures are suggested by a group of experts who do their best to decide which measure would have the desired impact. The best we can do is to trust their judgment. There are several other factors that will ultimately help. We'll hopefully soon have medication which will reduce the number of fatalities as well as the duration of hospitalization. Antibody tests, when available, will allow to identify the people who are immune to COVID-19, allowing those individuals to resume a normal life as they won't contract the disease anymore nor infect other people. These measures should allow the government to reduce confinement measures in due course. To summarize these observations, we have represented on the same graph the number of fatalities for the different scenarios. We then clearly see that doing nothing or having a poor confinement leads to many more fatalities than having a good or targeted confinement. Looking at a similar graph for the number of contaminating individuals, we see that a good confinement can lead to the smallest number of fatalities and a relatively short epidemics, but the confinement then has to last for the entire population. A targeted confinement, on the other hand, leads to a larger number of fatalities and lasts a similar length of time, but for a confinement which is mostly restricted to the vulnerable population. Once again, the figures presented here are just illustrative, as no confinement measure is perfect, and it is very likely that this measure will be adjusted as the epidemic progresses. Moreover, all our investigations were performed assuming that the fatality rate is 1%, a commonly accepted estimate. Should it be bigger, the number of fatalities will be larger and the epidemic will last longer. As a result, the outcome of the epidemic is likely to be worse than what is suggested here. The model we have used here are built using differential equation and treat the population as a generic whole. We can also develop computationally intensive agent-based models which use census data informed by social behavior to predict the effect that the confinement measures will have on the infected rate, but this will be for another video. So, what can we conclude from all this? First of all, it is clear that the epidemic will last for several months. The confinement measures should reduce the infection rate and so reduce the pressure on hospitals. They will also reduce the number of fatalities. More importantly, the decision measure that we take for ourselves are also protecting others, and it is our individual responsibility to be as careful as possible, regardless if we are considered at relatively high risk or not.